These equations are considered two of the most beautiful formulas in all of mathematics, Euler's formula and Euler's identity. And whether you are seeing them here for the very first time, or maybe you've seen them lots of times, I think you'll learn plenty of new things from this video. I actually have a bit of a different perspective on this than some of the other content that I've seen out there. My area of specialization for my PhD was complex analysis. And so certain complex analytic ideas, especially the idea of a complex derivative, those are going to play an important role here. Now, I remember seeing these formulas for myself the first time back in high school. I looked up the word math in the encyclopedia, the M encyclopedia. And these formulas were there, as well as the power series formulas for sine and cosine and e to the x. And it was all very fascinating and yet also kind of mind-boggling. I remember just being kind of confused, like what is going on here? So let's take, for example, the number e. What do we think of when we think of the number e? Well, maybe something from calculus, but also exponential growth. And then sine and cosine we tend to think of in terms of triangles or maybe the unit circle. And then of course we also have the number I here, the square root of -1, the imaginary number. And then down in Euler's identity, we also see pi. In fact, we have three hugely important numbers in math, all kind of combined together in Euler's identity, e, I, and pi. And sometimes this identity, by the way, is written as e to the I pi plus 1 equals 0. And where it comes from is by just plugging in pi for theta into Euler's formula. And so the real question is, where does Euler's formula come from? Oh, and remember that sine of pi is 0 and cosine of pi is -1. So all these different ideas are combined together into Euler's formula. And then Euler's identity is interesting in its own right, even apart from Euler's formula. So one of the questions we could ask is, what is the number e doing here? Because, for example, 2 to the I pi is not a nice number. It's this crazy looking decimal of a complex number. And 3 to the I pi is not nice. But e to the I pi works out so nicely, so cleanly, it's just -1. So what is e doing here? And then we could ask the same thing about pi and I in Euler's identity. And while we're at it, what does it even mean to have the number I as an exponent? Because, for example, I to the third power, that would make sense, right? That's just I times I times I. But 3 to the I, what does that even mean? Does that mean multiply 3 by itself I number of times? Well, I would like to suggest to you that we can think of these formulas as arising from that primitive notion of repeated multiplication. So 2 to the third power, remember, just means 2 times 2 times 2. That's repeated multiplication. But these formulas arise from that primitive notion of repeated multiplication, along with the fundamental property of exponents that's derived from it. And we can ultimately end up with these formulas. So with sine and cosine, you might wonder, well, how did they arise from just those basic ideas? Well, the traditional way that this is explained, the way that Euler came up with when he discovered Euler's formula, was the method of power series. And this power series approach is so elegant and so beautiful. And in fact, I'd be remiss if I did not show that to you, and I will in a minute. But the power series approach still kind of leaves you scratching your head a little bit. It's almost like it pulls a rabbit out of a hat, and you just end up getting sine and cosine here. So I would also like to give you a more nuts and bolts approach, where we just build up from that primitive notion of repeated multiplication, along with this fundamental property of exponents, to build up these exponential functions. So first of all, to build up real exponential functions, so like 2 to the x and 3 to the x and e to the x, but using that same procedure to also build up complex functions, e to the z, 3 to the z, 2 to the z, those functions. So how do we end up getting sine and cosine associated with e just from those primitive notions? Well, that's what we're going to see. And along the way, we're also going to encounter the complex derivative. Okay, what does it mean for a function to be complex differentiable? And this is such an amazing concept, and it's really at the foundation of all of complex analysis, is this idea of a complex derivative. And it has such far-reaching and really profound consequences, things that you wouldn't imagine if you're just thinking of real functions and derivatives of real functions. And so I'm very excited to be sharing that with you. The power series approach begins with these incredible little formulas here for sine, cosine, and e to the x. So for example, sine of x is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. And if you haven't seen these before, then first of all, your eyes might be kind of bugging out of your head a little bit, like, what am I seeing here? But we can kind of think of these power series as being like infinite degree polynomials, if there were such a thing. And what this is saying is that for every real number x, the left-hand side equals the right-hand side. And not just approximately, but exactly. So if you were to plug in a specific value for x, like x equals 0, or maybe x equals pi over 6, or 2.4, or whatever, the left side will equal the right side. And notice that the right-hand side will be an infinite series. So what's really going on here? Well, if we wanted to approximate the sine function near x equals 0 with a line, the line of best fit would be y equals x. It's really just the tangent line at x equals 0. And if we wanted to find a quadratic approximation at x equals 0, we couldn't do any better than just this line y equals x. But if we wanted a cubic approximation, so basically if we wanted to cook up a cubic polynomial that best approximates sine near 0, we would end up with x minus x cubed over 3 factorial. And it's actually not too hard to come up with this if you just know a little bit of calculus. Just write out the general form of a third degree polynomial and just take derivatives. And then find the constants a, b, c, and d that make the derivatives at 0 agree with the derivatives of sine at 0. And then keep doing this with higher and higher degree, and notice what happens. We're getting the beginning part of the power series expansion for sine. And we have these curves that approximate sine really, really well, not only near 0, but farther and farther out. And if we allow this to go up to infinity, so we get the power series for sine, it's just equal to sine of x for all x. So that's pretty cool. And we can do the same thing with cosine. And notice that with cosine, we only get even degree terms. And that's because cosine is an even function. Its graph is symmetric with respect to the y-axis. So for cosine, we have this parabola that approximates it well at x equals 0. And then we can do the same thing that we did with sine and get higher degree polynomials that ultimately converge to cosine. And the same thing works for e to the x. Here we have the tangent line at x equals 0, then a quadratic, a cubic approximation, and so on. Now, one of the great things about power series is how well they can be manipulated. Remember that the derivative of sine is cosine. Well, if we were to take the derivative of this power series for sine, we get the power series for cosine. The derivative of x, of course, is 1. It turns out that the derivative of negative x cubed over 3 factorial ends up being negative x squared over 2 factorial. And you can check that. Remember that 3 factorial is just 6. It's 3 times 2 times 1. And it might take a minute to verify this for yourself, but the same thing happens for all of the terms. And it's also the case that the derivative of e to the x is e to the x, and you can check for yourself. If you take the derivative of this power series term by term, you get the same power series back again. And if we wanted to find the power series for, say, e to the 5x, we could just take each of the x's in the power series for e to the x and replace them with 5x. And we'd end up with this. So instead of 1 plus x squared over 2 factorial and so on, we'd have 1 plus 5x quantity squared over 2 factorial. And you could simplify the terms and you'd end up with this down here. Well, Euler's great idea was to replace the x here not with 5x, but with ix. And when you do that, you get e to the ix is 1 plus ix quantity squared over 2 factorial plus ix cubed over 3 factorial and so on. And then we can simplify the terms. So for example, ix quantity cubed is just I cubed times x cubed. But what is I cubed? Well, there's a good chance you've seen this before. The powers of I go in cycles of 4. So I to the 1 is just I squared is negative 1, I cubed is negative I, and I to the 4th is 1. And that cycle just repeats itself. I minus 1 minus I 1. I minus 1 minus I 1. And so now if you work this out, notice that every other term is going to still have an I in it, and every other term won't have an I. Well, if we take the terms that don't have an I and move them out front, and then keep the terms that do have an I out in the back, but then factor out the I, notice what we get. And this is just beautiful. You should really try this for yourself with a pencil if you've never done it. Notice that this is the power series for cosine, and then plus I times the power series for sine. So e to the ix is cosine x plus I sine of x. And this whole derivation is just so aesthetically pleasing. It almost seems more like the work of an artist than a mathematician. So e to the ix is cosine x plus I sine of x. And of course, we can use theta instead of x, and we get our identities. But is there a way to get here without using power series, just starting from the idea of exponents? So our goal here is to be able to define e to the z for a complex number z, as well as like 2 to the z and 3 to the z, using a similar procedure to how we define e to the x, 2 to the x, 3 to the x for a real number x. Now, it's sometimes said that when we have a non-real exponent, we can't think of this any longer as being repeated multiplication. But that's also the case with real exponents. I mean, does 2 to the 4.7 really mean multiply 2 by itself 4.7 number of times? Or 2 to the negative third mean multiply 2 by itself negative 3 number of times? So strictly speaking, the idea of repeated multiplication is only valid when the exponent is a positive integer. So let's talk real quickly about how we build up the function 2 to the x, how we define 2 to the x for real values of x. And we'll show how a similar procedure can be used to build up 2 to the z. And we'll show ultimately how this gives us Euler's formula. So if n is a positive integer, we just define a to the n by repeated multiplication. And from this we get, for example, that 2 to the third times 2 to the fourth is equal to 2 to the seventh. And in general, it just follows from the definition that if m and n are positive integers, then a to the m times a to the n is equal to a to the m plus n. And we can kind of think of this as the fundamental property of exponents. And the question is, how should we define things like this, like 2 to the 0, 2 to the negative fifth, and so on, if we want this fundamental property of exponents to still hold? So let's take 2 to the 0. Well, of course, we know it's going to be 1, but why 1? Well, if we take 2 to the 0 and multiply it by, let's say, 2 to the fourth, then if our property of exponents is still going to hold, this should be 2 to the 0 plus 4, which is just 2 to the fourth. So we see that 2 to the fourth times 2 to the 0 gives us 2 to the fourth back again. So 2 to the 0 has to be the multiplicative identity. It has to be 1. So we are forced into defining 2 to the 0 to be 1 if we want our property of exponents to still hold. And say 2 to the negative fifth, how should that be defined? Well, 2 to the negative fifth times 2 to the fifth should be 2 to the negative 5 plus 5 if our property is still going to hold. And that's just 2 to the 0, which we saw must be 1. So 2 to the negative fifth has to be 1 over 2 to the fifth, the multiplicative inverse of 2 to the fifth. And in general, a to the negative n must be 1 over a to the n. And for something like 2 to the 1/3, we do a similar thing. Just multiply 2 to the 1/3 times 2 to the 1/3 times 2 to the 1/3, and that should be 2 to the 1/3 plus 1/3 plus 1/3 if our property is still going to hold. And that's just 2 to the 1, which is 2. So 2 to the 1/3 has to be the cube root of 2. And in general, a to the 1 over n has to be defined to be the nth root of a. And you can use similar reasoning to show that a to the m over n has to be defined like this. Now, so far we've extended our definition of exponentiation to cover the case when we have a rational exponent. But what about irrational exponents, things like this? Well, in this case, believe it or not, our property of exponents that we want to hold doesn't actually force us into defining these in any particular way. But if we want the function f of x equals 2 to the x to be nice in any kind of way, so if we want it to be continuous or differentiable or whatever, then we are forced into defining 2 to the x in a particular way, the way that we're familiar with. In fact, here's our function 2 to the x defined for rational inputs x. And it's not at all obvious, but you can get some kind of monstrosities of functions that extend this function to all reals and still satisfies this fundamental property of exponents. But there's only one nice way to do it, and that's this extension. In fact, if we just insist that our function is continuous at even one point, let's say x equals 0, then that one condition, along with insisting on our property of exponents, ends up giving us continuity everywhere. Okay, now that was a bit technical there at the end, but what we're really interested in is, what do we do with a complex exponent? So we've defined these real functions, f of x equals a to the x, and we're assuming here that a is a positive number. We've defined these in such a way that they satisfy, and this is sometimes referred to as a functional equation. F of m plus n equals f of m times f of n. And this kind of encodes our property of exponents into the function. So we would like to do the same type of thing to define f of z equals a to the z, where z is a complex number. And here, just like for the real case, to keep things simple, we'll just assume that a is a positive real number. So we want this function, first of all, to satisfy the functional equation, f of z plus w equals f of z times f of w, for all complex numbers z and w. And this, again, just encodes our property of exponents into the function. And second, we want the function to agree with the real function a to the x for real inputs x. Now, it turns out, though, that these two conditions alone aren't enough to guarantee us a unique function. Just like the real case, we needed that additional assumption of continuity. So we'll make one additional assumption here, that the function is differentiable, complex differentiable, at 0. Now, this assumption that it's differentiable at 0 and that it satisfies the functional equation is going to end up implying that f is differentiable everywhere. But we're only going to assume this much smaller condition, that its derivative at 0 exists. Now, the special case that a is e is ultimately what we're interested in. So let's take a look at that first. So we want to be able to define e to the z so that it satisfies these three conditions. Then these conditions will mean that if z is x plus iy, then we can write e to the z as e to the x plus iy. And then our property of exponents, our functional equation, tells us that this has to be e to the x times e to the iy. And we already know how e to the x is defined for real x. So the only remaining question, but it's a very big question, is how do we define e to the iy? And I claim that these three conditions are going to imply that e to the iy must be cosine of y plus I sine of y. So why is that? Well, it's going to depend vitally on this idea of a complex derivative, which I'll explain in a minute. But first of all, complex functions are notoriously difficult to visualize. Even something simple like f of z equals z squared, which you might think, oh, the graph is just a parabola, but that's not correct. The graph actually lies in four-dimensional space because it takes a two-dimensional input, like 2 plus I, which can be thought of as the ordered pair 2, 1, and gives a two-dimensional output. So a function from the complex numbers to the complex numbers is like a function from R2 to R2. So the graphs are like two-dimensional surfaces that lie in four-dimensional space. So they're very hard to picture in your mind. But one way to visualize a complex function is like this, to show where f of z is for a given input z. And by the way, we're looking at the complex plane here. So this is the real axis. This is the imaginary axis. We can plot complex numbers. So this point here, 5, 2, is really 5 plus 2y. So for a given function f, if we move z around, we can look to see what happens to f of z. So that's one way to visualize a complex function. Now, for our function e to the z that we want to define, remember that it has to agree with the real function e to the x on the real axis. So when z moves along the real axis, e to the z moves on the real axis. When z is, say, 0, remember that e to the 0 is 1. And notice that when we move our input to the right, we're getting this kind of exponential growth. And moving the other way, we get exponential decay. By the way, a similar thing happens for 2 to the z and 3 to the z. Notice that 3 to the z moves a little faster than e to the z because 3 is bigger than e, so we get faster exponential growth, and 2 to the z moves a little slower. Now, the big question is, what's supposed to happen to these functions if we move off-road here? In particular, if we move up the imaginary axis, what's going to happen? Well, we're going to end up getting this circular motion. And the big question is, why? Why should exponential growth in the real direction produce circular motion when we move in the imaginary direction? And by the way, this circular motion is what's going to end up getting sine and cosine involved, because we'll be on the unit circle. And another thing to notice is the rate at which these points are moving on the unit circle. Notice that 3 to the z moves fastest 2 to the z slowest, and e to the z in the middle. In fact, we're going to see that if the input is moving at a constant unit rate up the imaginary axis, so say 1 unit per second, then e to the z moves at exactly the same rate, that unit rate. And this ultimately will come from the fact that e is a very special number. So here are the graphs of y equals e to the x and y equals 2 to the x. And of course, we're not looking at the complex plane anymore. This is just the ordinary xy plane. But notice the curves have different slopes at x equals 0. E to the x is a little steeper. For e to the x, the slope is exactly 1. In fact, some books use this as a definition of the number e. It's the unique base of an exponential function that has a slope of 1 at x equals 0. And this is ultimately going to be the reason why e to the z moves at exactly the same rate around the unit circle that z does up the imaginary axis. Now, I haven't shown why any of this is true yet. Why, when z moves up the imaginary axis, we go around on a circle, and why e moves at this unit speed around the circle. But let's assume, for now anyway, that it's true. What does this imply? Well, as z moves up the imaginary axis, then at any given moment, the distance that e has traveled will be the same as the distance that z has traveled, since they're moving at the same rate. But remember that the unit circle has a circumference of 2 pi, so to get halfway around the circle, we need to go a length of pi. And this means that when z goes up a length of pi, so it's at pi I, then e to the z will have moved to -1, or -1 plus 0i. So e to the pi I is -1. That's Euler's identity. So notice how e, pi, and I all work together here. We needed e so that we move at a unit speed. 2 to the pi I and 3 to the pi I don't work. We need pi because the length of the top half of the unit circle is pi. And I haven't really explained why we need I yet, but let me just say that when you multiply a complex number by I, it rotates the complex number by 90 degrees. And this 90-degree rotation is ultimately what's going to cause us to be on this circular path in the first place. And that's one of the key ideas, so it's something I want to take a little bit of time to explain. Now, if all these things we've been talking about are true, and that's something we still need to show, but if this is all true, then we will also get Euler's formula out of all this. And here's why. So let's suppose we go up a length of theta, so instead of pi, just some other length theta. So we're at some point z, and z is really just I theta. Well, then just from what we were talking about earlier, this length over here, this distance, has to be the same as this length, this distance. And so this length also has to be theta. But just by the definition of radian, what it means to measure an angle in radians, this angle is theta. And again, that's really just the definition of the radian measure of an angle. Well, if this is theta, then just by the definition of sine and cosine, this point is cosine theta comma sine theta. So we get that e to this point here, e to the I theta, is this point, cosine theta plus I sine theta. So notice we end up with Euler's formula. And of course, we have the special case of theta being pi that gives us Euler's identity, but it really works for any theta. Now, all this has been big picture stuff. We haven't gotten into all the details of why, for example, exponential growth in the real direction should produce circular motion when we go up the imaginary axis. And also why e moves at that unit rate. I gave the basic idea that it's because e to the x has a slope of 1 at x equals 0, but I didn't really explain what was going on. So what remains to be shown? Well, just to be clear here about where we're headed, remember our goal is this: to be able to define e to the z in such a way that it satisfies this functional equation. So in other words, we want e to the z plus w to be e to the z times e to the w. And we also wanted to agree with the real function e to the x. It wouldn't make any sense to define it in a way where, say, e to the fifth no longer means e to the fifth. And we also have this last condition that its complex derivative at 0 exists. And as I mentioned earlier, this will all mean that if z is x plus iy, then e to the z is e to the x plus iy, and condition 1 will imply that this equals this. And the claim here is that these conditions will imply that e to the iy has to be cosine y plus I sine of y. So what we want to show is that there not only exists a function f with these properties, but that that function is unique. and that it is this function. There aren't two different functions that satisfy these properties. So the only reasonable way to define e to the iy is like this. But why, for example, couldn't we just define e to the iy to be 1? So in other words, we just define e to the z to be e to the x. So for example, e to the 4 plus 7i would just be e to the 4th. In other words, we just ignore the imaginary part. And you might think, yeah, that would be dumb, but at first glance, there doesn't seem to be anything wrong with this as far as our three conditions go. If you take a second to think about it, you'll see that this function, the function f of z equals e to the x, would satisfy those first two conditions, and it seems like there should be no problem with the function being differentiable. And yet that's where the problem is going to be. So we need to understand this idea of a complex derivative. And part of my purpose here is not just to explain where Euler's formula comes from, but to also explain the complex derivative, which is central to really everything in complex analysis. And it's also going to give us Euler's formula and identity. So here's our definition of derivative. For a complex function f, the derivative at z is defined like this. Now, you might be thinking, what's so big about this? This is just the same definition we use for real functions back in Calculus 1. And yeah, that's actually part of the magic of it. It's the same formula, but what it means is much deeper. Now, it's sometimes said that what makes this definition so powerful is that since h is a complex number, h can approach 0 from infinitely many different directions, not just from the left and the right. And while that's true, that's not really the main story. The real power comes from the fact that we can divide by h, a number that's like a two-dimensional vector. It has both length and direction, a complex number. That's something we can't do in ordinary multivariable calculus. So for a function from like R2 to R2, you can't divide by a little two-dimensional vector h. There's no natural notion of 1 over h when h is a vector. But since the complex numbers form what's called a field, we can divide by h. And this has some shocking consequences. In fact, at the end of my next video, I'll give you a really mind-blowing fact about complex differentiable functions. Now, this is part one of a two-part video series on Euler's formula and identity. And in the second video, one of the things that we'll be looking at is the geometry of the complex derivative. What it means geometrically or graphically to say that a function is complex differentiable. And then, of course, we'll relate all of this back to Euler's formula. But there's one more thing that I want to show you here. I'd like to show you real quickly that these three conditions on a function f will imply that f is complex differentiable not just at 0, which is our third condition, but that it's complex differentiable for all values of z, and that f prime of z is equal to f of z. And this should remind us of the fact that we know from calculus that the derivative of e to the x is e to the x, the real derivative of e to the x. Well, this is saying that the complex derivative of e to the z will turn out to be e to the z. So why is this? Well, if f were complex differentiable, which we don't know just yet, but let's assume it for the moment, then we would have this. But then f of z plus h is just f of z times f of h by the functional equation, condition 1. And then we can factor out the f of z. In fact, it'll come completely out in front of the limit because it's constant with respect to the limit. There are no h's here. But then we can rewrite it like this. Notice that f of h is just the same as f of 0 plus h, and 1 is just f of 0. Now, why is f of 0 1? Well, because by condition 2, f agrees with the real function e to the x for real inputs, and e to the 0 is 1. But notice what we have here. This is just the definition of the complex derivative at z equals 0. It's just f prime of 0. I mean, look at the definition of f prime of z and just let z be 0, and this is what we get. But we're assuming that f prime of 0 exists. That's condition 3. So what does this tell us? Well, remember that we didn't know that f prime of z up here exists. In other words, we didn't know that this limit exists. But the fact that we know that this limit exists means that we can work backwards to say that this limit exists and keep going backwards. And finally, we get that this limit exists, and therefore f is complex differentiable at z. So the fact that f is complex differentiable at 0, and that it satisfies the functional equation, and that it agrees with the real function e to the x, ends up implying that f is complex differentiable at all values of z. And more than that, what is f prime of 0? Well, I claim f prime of 0 is 1. And so we'll get f prime of z is equal to f of z. Now, why is f prime of 0 1? Well, this is going to make more sense after seeing the next video when we talk about the geometry of the complex derivative. We're going to really visualize things. But to say that this limit exists means that it exists and has the same value no matter how h approaches 0. Remember that h is a complex number and it can approach 0 from many different directions. But in particular, the limit should exist and have the same value if h approaches 0 just through the real numbers. But then we just have the real derivative of the real function e to the x at x equals 0. That's what this would be if h were real. And that derivative is 1. So in other words, the fact that the real derivative of the real function e to the x at x equals 0 is 1 means that this complex derivative will also be 1. And again, this will make more sense after seeing the next video. Oh, and by the way, we should also be keeping in the back of our mind how this would work for a general positive number a, not just a equals e. Well, everything here would be exactly the same up until the very end here. F prime of 0 would be the derivative of a to the x when x equals 0. And remember, the derivative of a to the x is a to the x times natural log of a. So f prime of 0 will be natural log of a. And f prime of z would be f of z times natural log of a. And of course, when a is e, this is just 1. Finally, I'm still just kind of starting out this YouTube channel, doing the best that I can. And so if you put a like or a comment on the video, I'd really appreciate that. I've heard that comments in particular are good for the algorithm, for pushing out the video to as many people as possible. So maybe if there's a video topic that you'd like to see or just a comment in general, I would love to hear that. So in the next week or two, when I finish making part 2 of the video, I'll put that on the end screen here. But thank you for watching and have a great day.